In this video, I'll find the electric field that's created by a +8 nanocoulomb charge at 3 different locations. Here I've called them A, B, and C, and I have indicated their positions here. So we're looking for the electric field at, this would be A, R is 4 meters, so radius 4 meters, theta is 0 degrees. 0 degrees is horizontal. I've drawn a +x and +y axis here. So the 0 degrees is on the x-axis. So that's this one, A. B is at a radius of 5 meters with theta equals 45. So 5 meters is up here and 45 degrees from 0. And then the third one is at the position x equals 4 meters, y equals -3 meters. So that's this one down here, 4 meters in the +x direction, 3 meters in the -y direction. So to find the electric field at these 3 locations, we need to know that the magnitude of the field is kq over r squared. To find the direction of the field, we know that this is a positive charge and all the field lines go directly out from positive charges. So at each of these locations, the direction of the electric field is directly away from that. So there's the electric field at A, this direction, electric field at B, and then that direction is the electric field at C. So let's find what those are. K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So E, if we start with A, so that means the magnitude of E at A is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times Q. Q is this charge. So +8 nanocoulombs over r squared. R squared, r is the distance from the charge to the position we're talking about. So that's 4 meters. Check our units. Meters squared on the top, meters squared on the bottom. This coulomb cancels one of those coulombs. 10 to the 9th, this is nano, that's 10 to the -9. So that 10 to the 9th cancels out this nano. This is 4.5 newtons per coulomb. So that's the magnitude. So now for the direction. This gives the magnitude. I should have put this in here even though I made all of these positive. The direction, theta was 0 degrees, so the electric field also is in the 0 degree direction. So I can call this actually the vector if it's that at 0 degrees. Alright, so there is the first one. Now the second one, B. So EB is, same thing, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times 8 nanocoulombs divided by, this time, this distance r, this is 5 meters. So 5 meters squared. And if we want to give it the direction already, we can say the vector of it is up and to the right, the same angle that this was. So at 45 degrees. 2.88 newtons per coulomb at 45 degrees. That's the second one. Now for the third one. EC 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Same 8 nanocoulombs. Divide by, now the distance from here to there, that's this distance. So to find that, we can use the Pythagorean theorem. So c squared equals a squared plus b squared. So that means c, if we call this c, c equals 4 meters squared plus 3 meters squared square root, which is 5 meters. At what angle? Well, this angle, theta, I know the tangent of theta is opposite over adjacent, so 3 over 4. So theta is inverse tan of 3/4. And that gives me 37 degrees. So I know this theta is 37 degrees, but it's in the negative direction from 0. So it's actually at negative 37 degrees. Another way you could do it is to say that the tangent of theta is actually minus 3 over 4. And if you do that, it will give you that theta is negative 37 degrees. So you could put that in. I don't like to do it that way because if I did, and I was over here, this would be 3, so in the positive y direction, 3 over negative 4. And again, when I did the inverse tangent, I would get negative 37 degrees, which is not the right answer. Negative 37 is down here. In fact, it would be 180 degrees away from that. So the way I like to do it is always just use the triangle itself without negatives and positives, then figure out which direction it's going from where. And so I take this 37 degrees, figure out that it's negative from 0. So that's this. So this would be, this is actually the same thing. So 2.88 newtons per coulomb at negative 37 degrees. If we want to then break it back up into the x and y components, then we can do that. So this is 2.88 newtons per coulomb. Let's see. The horizontal direction of it, this would be times cosine of that theta. Cosine of 37 degrees in the x direction plus 2.88 newtons per coulomb sine of 37 degrees. So you could also say this is 2.88 newtons per coulomb times the cosine of negative 37 degrees from here, because cosine of positive 37 and cosine of negative 37 are the same. Then this could be plus 2.88 newtons per coulomb times the sine of negative 37 degrees, because the sine of negative 37 is opposite the sine of positive 37. So whichever way you like to do it. And I should have added here, that one's in the y hat direction.